the shape of the observable universe, a cosmic journey to the edge of time and space. Part 1. The Geometry of Reality. Welcome. Welcome to this journey through the cosmos, a voyage that will transport your mind across billions of light years, backward through billions of years of time, into the deepest mysteries of existence itself. As you settle into a comfortable position, as you allow your body to relax and your breathing to slow, let your consciousness drift outward, away from the concerns of daily life, into the vast expanse of space and time that surrounds us. This is a story about shape. It is a story about geometry. It is a story about the fundamental architecture of reality. Throughout this extended meditation, we will explore the universe from the smallest scales we can measure to the grandest vistas our instruments can perceive. We will examine the ancient light that fills all of space. We will trace the vast filaments of matter that stretch across billions of light years. We will contemplate the mysterious forces that drive cosmic expansion. And through it all, we will return again and again to a single profound truth. The universe has a shape, and that shape determines everything. Let us begin at the foundation, at the most basic level of cosmic geometry. Our universe is spatially flat. This statement, while simple, contains within it centuries of human curiosity, decades of careful observation, and some of the most sophisticated mathematics ever developed. Spatial flatness is not a metaphor. It is not a poetic description. It is a precise geometric fact confirmed by the most careful observations scientists have ever made. Imagine, if you will, a perfectly flat plane extending infinitely in all directions. No curves, no bulges, no warping. Just a perfectly smooth, endless surface. That, in essence, is the shape of our universe on the largest scales. When we measure distances and angles on cosmic scales, when we look at the geometry of space itself, we find that space behaves like this perfectly flat plane. Lines that are parallel remain parallel. The angles in a triangle add up to exactly 180 degrees, no more, no less. This is the Euclidean geometry we learn in school, projected onto the entire cosmos. But how do we know this? How can we possibly measure the shape of the entire universe? The answer lies in patient observation and brilliant mathematical analysis. One of the most powerful tools for understanding cosmic geometry is the observation of the cosmic microwave background, the ancient light that has been traveling through space since nearly the beginning of time. The flatness of the universe is confirmed by careful analysis of the angular size of fluctuations in the cosmic microwave background. The cosmic microwave background is not perfectly uniform. It has tiny variations in temperature from place to place, variations of about 1 part in 100,000. These variations are very subtle, but they are measurable using sensitive instruments. When astronomers analyze the pattern of these variations, looking at how frequently they occur at different angular scales across the sky, they can extract information about the geometry of the universe. In a flat universe, these temperature fluctuations have a specific pattern of angular sizes. In a closed universe, curved like the surface of a sphere, the pattern would be different. In an open universe, curved like a saddle surface, the pattern would be different again. By comparing the observed pattern of temperature fluctuations to theoretical predictions for different geometries, astronomers can determine which geometry matches reality. The observations show with remarkable precision that our universe is indeed flat. The angle of curvature is so close to zero that it is consistent with perfect flatness within the limits of our ability to measure. The universe, as far as we can tell, has no curvature at all. This flatness is a remarkable fact. It is not obvious why the universe should be flat. In principle, it could have been curved, either closed or open. The fact that it appears to be flat to such high precision suggests something interesting about the early universe and how it came to be. Modern cosmology suggests that an early period of rapid expansion called inflation stretched the universe and flattened it out, much as inflating a balloon stretches and flattens any bumps on its surface. This inflation theory is supported by the observed flatness of the universe. Yet even within a flat geometry, there is more complexity than might be apparent. The universe could possess what physicists call a multiply-connected topology. Topology is different from geometry. Geometry describes the local curvature of space at each point. Topology describes the overall structure and connectivity of space. A flat sheet of paper and a flat torus or cosmic donut have the same geometry at every point, but very different topologies. The sheet has a single, simply connected topology. The torus has a multiply-connected topology where traveling far enough in one direction brings you back to where you started without ever reaching an edge. The universe could have a torus topology or other exotic topologies while still being geometrically flat. In such a universe, the laws of physics would be the same everywhere. Light would travel in straight lines by local measures, but the global structure would be peculiar. Travel far enough in one direction, and you might find yourself approaching yourself from the opposite direction, approaching an image of yourself traveling away. Despite decades of searching, despite the most sophisticated instruments and mathematical tools at our disposal, we have found no evidence for a multiply-connected topology. We have not detected any indication of the universe folding back on itself. The universe appears to have a simple, simply connected topology, extending without repeating, without closing back on itself. But we must remain open to the possibility that future observations might reveal a more complex topology. The universe, it seems, still has secrets to reveal. What constrains the shape of the universe? What fundamental principles determine whether the universe is flat or curved, simply connected or multiply-connected? The answer lies in two great frameworks of modern physics. The first is general relativity, Einstein's revolutionary theory of gravity and space-time, developed over a century ago, but still the best description we have of how gravity works. General relativity tells us that the geometry of space is not fixed and absolute, as Newton thought. Rather, the geometry is determined by the distribution of matter and energy. Matter and energy curve space-time. The curvature of space-time determines how gravity works. The second framework is the cosmological principle. This principle states that the universe, on the largest scales, is both isotropic and homogeneous. Isotropic means it looks the same in all directions from any given location. Homogeneous means it looks the same from every location. In other words, there is no special place in the universe. Every location is equivalent. This principle is deeply embedded in how modern cosmologists think about the universe. It is not proven absolutely, but it is supported by observations. The cosmic microwave background appears isotropic. The distribution of galaxies appears homogeneous on the largest scales. Together, general relativity and the cosmological principle constrain the possible shapes the universe can take. Given these two principles, only a few geometries are possible. The universe could be flat, closed, or open. It could have a simple topology or a more complex one. But the combination of observed flatness and the symmetry requirements of the cosmological principle narrow down the options. The universe we live in appears to be spatially flat with a simple topology, extending infinitely in all directions without edge or boundary. But why does the shape of the universe matter? Why should we care whether it is flat or curved? The answer is that the geometry of the universe affects everything. It affects how light propagates through space. It affects how structures form and evolve. It affects the ultimate fate of the universe. In a flat universe, expansion will continue indefinitely. In a closed universe, expansion might eventually reverse, pulling all matter back together in a big crunch. In an open universe, expansion would continue forever, but more gently than in a flat universe. The geometry of the universe determines the destiny of the universe. The geometry also affects the formation of structures on the largest scales. Dark matter and ordinary matter cluster together under gravity, forming galaxies, groups, clusters, and the cosmic web. But the underlying geometry affects how these structures form and how they are arranged. The geometry enters into the equations that govern structure formation. It appears in the formulas that predict how density fluctuations grow and evolve. To understand the cosmic web, we must understand the geometry in which it forms. To test whether our understanding of cosmic curvature is correct, astronomers use ingenious observational methods. One such method involves measuring cosmic triangles. By observing distant galaxies and carefully determining their positions in three-dimensional space, astronomers can essentially draw triangles across billions of light years. In a flat universe, the angles of these triangles add up to exactly 180 degrees, just as they do on a flat piece of paper. If the universe were curved, the angles would add up to more than 180 degrees in a closed universe, or less than 180 degrees in an open universe. By carefully measuring these cosmic triangles, astronomers test the universe's geometry directly. Another powerful method is gravitational lensing. This technique exploits the fact that massive structures curve spacetime and thus bend light passing near them. Just as a glass lens bends light, so too does the curved spacetime created by massive objects. By observing how light from distant objects is bent as it travels toward us, astronomers can map the distribution of matter, both visible and dark, along our line of sight. They can measure the amount of bending and use this information to test predictions about cosmic geometry. Gravitational lensing has become one of the most powerful tools in modern cosmology for mapping the distribution of matter and testing our understanding of gravity and geometry. Now, when we speak of the observable universe, we are speaking of something very specific. The observable universe is not the entire universe. It is the portion of the universe from which light has had time to reach us since the Big Bang. It is defined by the cosmic particle horizon, the maximum distance from which light can reach us. The observable universe has a very specific shape. It is a sphere, and it is centered on you, the observer. This might seem strange at first. It might seem to place you in a special, privileged location. But this is not the case. Every observer in the universe, no matter where they are, perceives themselves at the center of their own spherical observable universe. This is not because any location is truly special, but because this is how observation works. Light takes time to travel. The farthest objects we can see are those from which light had just barely enough time to reach us since the universe began. This creates a sphere around every observer. The center of this sphere is the observer. The radius of this sphere is the particle horizon, the distance that light could have traveled, given the age of the universe and the expansion history of the cosmos. For observers on Earth, for us, this particle horizon is approximately 46.5 billion light-years away. This is the radius of the sphere of the observable universe. Everything we can see, everything we can know through direct observation, lies within this sphere. Beyond this sphere lies mystery, lies the unobservable universe, lies everything that happened beyond our cosmic horizon. You might wonder about something that seems paradoxical. The observable universe is about 46.5 billion light-years in radius, but the universe is only about 13.8 billion years old. If light travels at its maximum speed and has been traveling for 13.8 billion years, it should have covered only 13.8 billion light-years. How can the observable universe be more than 3 times larger? The answer reveals something profound and beautiful about how the universe works. The observable universe is larger than the age of the universe times the speed of light because of cosmic expansion. The universe is not static. Space itself is expanding. While light was traveling toward us from distant objects, the space carrying that light was also stretching, expanding, pulling the light's origin point farther and farther away. By the time that ancient light reached us, having traveled for billions of years at the speed of light, the galaxy that emitted it was much farther away than 13.8 billion light-years. The light had traveled 13.8 billion light-years, but the expansion of space had moved the galaxy's current location to 46.5 billion light-years away. This is a subtle but crucial point. The expansion of space does not violate the cosmic speed limit. Light still travels at the speed of light through space, but space itself is expanding, creating new space, stretching existing space. This expansion allows distances to grow faster than light could traverse them. It is space itself that expands, not objects moving through space at superluminal speeds. The expansion continues constantly. Even now, even as you listen to these words, the observable universe is growing larger. New space is being created. The particle horizon is moving outward. The observable universe expands, not because new regions come into view, though that does happen, but because space itself stretches, because light has had more time to reach us from distant objects. This raises an important point about perspective. Every observer anywhere in the universe has their own observable universe. A being on a distant planet, billions of light years away, would perceive a different set of observable objects. Their observable universe would be centered on their location. Their cosmic horizon would encompass different galaxies and different regions of space than ours does. Not because their sky is fundamentally different, but because they are at the center of their own cosmic sphere. The observable universe is subjective in this sense, relative to the observer's location. Yet the underlying universe is objective and the same for all observers. The universe itself is not observer-dependent. Only our observational access to it is. Now let us contemplate the sheer scale of this observable universe that defines the limits of our cosmic home. The volume of the observable universe is approximately 3.58 times 10 to the 81st cubic meters. To even attempt to comprehend this number, imagine a cubic meter of space. That is a cube about the size of a large closet, about 1 meter on each side. Now imagine a billion such cubic meters. Now imagine a billion such collections. Now imagine a billion such super collections. And multiply that by about 200 billion. You would be approaching the number of cubic meters in the observable universe. Yet within this incomprehensibly vast volume, there is matter, there is structure. There are galaxies and stars and planets, and on at least one small planet orbiting one ordinary star, there is life. There is consciousness. There is the universe becoming aware of itself. This is perhaps the deepest mystery of all. How is it that the universe, having expanded from an infinitesimal point to something so vast, having assembled itself into galaxies and stars and planets, comes to produce conscious beings capable of contemplating their own existence? Part 2. Counting the Cosmos. As we venture deeper into our understanding of the observable universe, we begin to confront numbers so vast that they challenge our intuition and awaken our sense of wonder and awe. These are not idle numbers, not mere abstractions. These are measurements of the actual material content of the universe. These numbers tell us something profound about what exists. Let us begin with galaxies. The observable universe contains approximately 2 trillion galaxies. 2 trillion. That number alone deserves a moment of contemplation. If you were to count one galaxy per second, without sleeping, without resting, without pausing for a single moment, it would take you 63,000 years to count to 2 trillion. By the time you finished counting all the galaxies, if you somehow had the immortality to do so, the ones you counted first would have changed, evolved, merged with others, transformed into different forms. Each of these 2 trillion galaxies is not a single star, but an enormous island of stars separated from other galaxies by vast voids of space. The nearest large galaxy to our own Milky Way is Andromeda, about 2.5 million light-years away. That is 2.5 million light-years of mostly empty space between us and our nearest galactic neighbor. And yet Andromeda is close, relatively speaking. Most galaxies are much farther away. Within and among these 2 trillion galaxies dwell the stars themselves. There are approximately 10 to the 24th stars in the observable universe, 10 followed by 24 zeros. This number is so incomprehensibly large that it exceeds the number of grains of sand on every beach on every ocean on Earth, multiplied thousands of times over. Each of these stars is a sun, a massive ball of plasma held together by its own gravity, burning hydrogen through nuclear fusion at its core, converting matter into energy at a rate that would power human civilization for millions of years. Each star is capable of hosting its own planetary system. We know this because we have discovered thousands of exoplanets in orbit around distant stars. As our instruments improve, we continue to find more. Most stars probably host planets. Most of those planets are probably lifeless. But some might not be. Some might harbor life. Some might harbor civilizations. Some might harbor conscious beings who wonder, as we do, about the nature of the universe and their place within it. What is the substance that makes up all these stars and galaxies? The answer is matter, ordinary matter, the kind of matter you and I are made of, the stuff we can touch and see and understand. The total mass of ordinary matter in the observable universe is approximately 1.5 times 10 to the 53rd kilograms. This is a number so large that it is difficult to grasp. 1.5 followed by 53 zeros. Every kilogram represents about 2.2 pounds of matter. So the observable universe contains about 3.3 times 10 to the 53rd pounds of ordinary matter. Yet, and this is crucial, this represents only a small fraction of the total content of the universe. Most of the universe is not ordinary matter. Most of the universe is dark matter and dark energy, exotic forms of matter and energy that are invisible to our eyes, detectable only through their gravitational effects and their influence on cosmic expansion. Dark matter comprises about 27% of the universe's total mass and energy. Dark energy comprises about 68%. Ordinary matter comprises only about 4.8%. We live in a universe that is dominated by things we do not fully understand, things we cannot see directly, things we can only know through their effects on the things we can see. Within this vast amount of ordinary matter, certain elements are more abundant than others. Hydrogen is by far the most abundant element in the universe. Hydrogen is the simplest element, consisting of a single proton nucleus orbited by a single electron. The observable universe contains approximately 10 to the 81st hydrogen atoms, 10 followed by 80 zeros. This is more atoms than there are stars. In fact, stars are made mostly of hydrogen. Our Sun, a fairly large star, is about 73% hydrogen by mass. Hydrogen is the raw material from which stars are built. It is the fuel that powers stars through nuclear fusion. And it is the most abundant element, not only in stars, but in the universe as a whole. But the universe is not just matter and stars. It is also filled with light, with photons, with radiation. In fact, the universe is far more filled with light than it is with matter. The observable universe contains approximately 4 times 10 to the 84th photons. Photons are particles of light, the fundamental carriers of electromagnetic radiation. They have no mass, but they carry energy. They travel at the speed of light, which is, of course, the only speed at which photons can travel. These photons outnumber atoms in the universe by an astounding factor of about 1 billion to 1. For every atom in the universe, there are about 1 billion photons. Where do all these photons come from? The answer is that most of them come from a single source, the cosmic microwave background. The cosmic microwave background contains the vast majority of photons in the universe. This ancient light was emitted when the universe was only 380,000 years old, when matter and radiation decoupled, when the universe became transparent to radiation for the first time. These photons have been traveling through space ever since, for the entire 13.8 billion year history of the universe since the Big Bang. They have been redshifted by cosmic expansion, their wavelengths stretched, their energies diminished. But they are still there, filling all of space, a sea of ancient light in which all modern objects swim. The energy density of the cosmic microwave background is approximately 0.260 electron volts per cubic centimeter. An electron volt is a unit of energy commonly used in particle physics. It is the amount of kinetic energy gained by an electron when accelerated through a potential difference of 1 volt. 0.260 electron volts per cubic centimeter might seem like a small amount of energy, and indeed, compared to the energy density of matter or to the energy we encounter in everyday life, it is small. But remember that this is the energy density of the cosmic microwave background photons pervading all of space. There are a tremendous number of such photons in the universe. Their collective energy is significant. Looking at the larger structure and composition of the observable universe, we find that it is isotropic and homogeneous on the largest scales. This means that if you were to zoom out far enough, looking at regions billions of light years across, you would find that the universe looks essentially the same no matter where you are or which direction you look. There is no center to the universe. There is no privileged location. Every point in space is equivalent. Every observer anywhere in the universe would perceive roughly the same average properties of the universe. This universal homogeneity and isotropy is what we call the cosmological principle, and it is one of the deepest and most important assumptions in modern cosmology. When we measure the average density of the observable universe, taking into account all the matter spread throughout all of space, we find a striking result. The observable universe contains approximately 5 hydrogen atoms per cubic meter on average. 5 atoms per cubic meter. To put this in perspective, a cubic meter is about the volume of a large refrigerator. In such a volume, there are on average only 5 hydrogen atoms. Space is mostly empty. Space is the true vacuum of the universe. Matter is the exception, the rare clustering of atoms into stars and galaxies. And yet, we must be careful with our language. This is an average density. Matter is not uniformly distributed. Matter clusters together into galaxies and stars, leaving vast regions of space that are nearly empty. The density in the core of a star is incomprehensibly high, with billions of tons of matter compressed into a cubic centimeter. The density in a galaxy is higher than average. The density in a galaxy cluster is higher still. But the density in the voids between galaxies, the empty spaces that make up most of the universe's volume, is much lower than average. When we average all these densities together across the entire observable universe, we get this result: 5 hydrogen atoms per cubic meter. Perhaps the most striking fact about the composition of the observable universe is this: ordinary matter, the material you and I are made of, the stuff we can see and touch and understand, makes up only about 4.8% of the total mass and energy of the universe. Everything we see, all the galaxies and stars and planets and people, all the matter that forms the structures we observe, represents less than 5% of what exists. The remaining 95% of the universe is dark matter and dark energy. Dark matter comprises about 85% of all matter in the universe. It is invisible to our eyes. It does not emit light or absorb light or interact with light in any way that we have detected. It is detectable only through its gravitational effects. It provides the scaffolding upon which visible matter hangs. It shapes the large-scale structure of the universe. It holds galaxies together. It influences the motion of stars within galaxies. Dark energy comprises about 68% of the total mass and energy of the universe. It is even more mysterious than dark matter. Dark energy appears to have a constant density that does not decrease as the universe expands. It acts like a repulsive force, pushing space apart, accelerating the expansion of the universe. We do not know what dark energy is. We can write equations that describe its behavior. We can measure its effects. We can predict how the universe will evolve under dark energy's influence. But what it fundamentally is remains one of the greatest mysteries in physics. Together, dark matter and dark energy comprise 95% of the universe. They are the dominant components. They shape the universe's structure and its evolution. The ordinary matter, the visible matter, the matter that makes up stars and planets and people, is secondary. It is embedded in the dark matter scaffold. It responds to dark energy's expansion. We are the minority inhabitants of a universe dominated by invisible components. Part 3. The Cosmic Web. As we continue our journey through space and the structure of the universe, we must shift our focus from individual objects and abstract numbers to the grand architecture that connects them all. The universe is not randomly scattered. It is not uniformly distributed. Instead, matter in the universe is organized into a vast network that spans billions of light years, a structure of breathtaking complexity and sublime beauty. This structure is called the cosmic web. The universe is structured into what scientists call the cosmic web. This is not a web made of physical material like silk or wire. Rather, it is a network of matter and energy distributed through space according to the laws of gravity. The cosmic web is one of the most profound discoveries in modern cosmology. It is a revelation of how the universe is organized at the largest scales. It shows us that the universe is not just a random collection of objects scattered haphazardly through space. The universe is organized. It has structure. It has architecture. The cosmic web consists of several distinct components, each playing a crucial role in the grand architecture. There are filaments, thread-like structures of galaxies, gas, and dark matter that stretch across the universe like the strands of a web. These filaments are the highways along which matter flows, the backbone of the cosmic structure. There are clusters, dense regions where gravity has pulled matter together into some of the most massive structures in the universe. These clusters sit at the intersections of filaments, like spiders waiting in the centers of their webs. There are superclusters, vast groupings of clusters that span hundreds of millions of light years. And there are voids, enormous regions with very low galaxy density, vast empty spaces that are surrounded by filaments like bubbles in foam or like the spaces in a sponge. Filaments deserve particular attention because they represent the true foundation of cosmic structure. They are the most important components of the cosmic web. Filaments are thread-like structures made of galaxies, gas, and dark matter. They are not isolated features, not anomalies, but rather the dominant structures of the universe on the largest scales. These cosmic threads can be millions of light years long. Some of the largest filaments span tens of millions or even hundreds of millions of light years. They host hundreds of galaxies, sometimes thousands of galaxies. Along these filaments, matter flows under the influence of gravity, pulled toward dense regions, creating a vast network that permeates all of space, like the underground root system of some cosmic forest. Voids, by contrast, are regions with very low galaxy density. Sometimes they are nearly empty of visible matter, yet these voids are not entirely empty. They contain gas, dark matter, and the subtle effects of gravity. They are not true vacuums, not zones of complete nothingness. Rather, they are relatively empty compared to the filaments. Voids are surrounded by filaments like cells in a cosmic honeycomb. Together, filaments and voids create a structure that has been compared to the structure of a sponge or to the structure of a brain with its network of neurons, or to other organic structures that maximize surface area while minimizing total volume. Most galaxies do not reside in voids. Most galaxies live in filaments or clusters where the density of matter is higher, where gravity has had the strongest effect, where structures have had time to condense and coalesce. The voids are relatively empty, relatively devoid of galaxies and stars. The filaments are where the action is, where galaxies congregate, where stars are born, where the visible universe manifests. How did this cosmic web form? The answer lies in gravity and the nature of the early universe. The cosmic web forms due to gravitational instability acting on small density fluctuations. In the early universe, matter was distributed almost uniformly with only tiny variations in density from place to place. These variations were incredibly subtle, variations of about 1 part in 100,000. But these tiny variations were sufficient. Where density was slightly higher, gravity pulled in more matter, amplifying the variation. Where density was slightly lower, matter drained away, leaving voids behind. Over billions of years, these tiny variations grew into the grand structures we see today. Matter flowed into overdense regions, creating filaments and clusters, while leaving behind voids where matter had been depleted. This process is called gravitational instability. It is a fundamental process that operates throughout the universe, creating structure wherever there are tiny density variations. It is beautiful in its simplicity. You need only 3 things: gravity, matter, and time. Give matter billions of years to respond to gravitational forces, and structure naturally emerges. This is how galaxies formed. This is how clusters formed. This is how the cosmic web formed. The cosmic web is visible in large galaxy surveys, where astronomers have mapped the positions of millions of galaxies across vast regions of space. The Sloan Digital Sky Survey, or SDSS, has mapped millions of galaxies and determined their distances using spectroscopy. The 2DF Galaxy Redshift survey, conducted in the Southern Hemisphere, has done similar work. These surveys have revealed the cosmic web in stunning detail, showing the filaments, voids, and clusters in three-dimensional maps. These maps are perhaps among the most beautiful data visualizations ever created, revealing a structure of organic complexity, of surprising intricacy, of patterns that repeat at different scales. The largest known filament in the cosmic web is approximately 50 million light-years long. This is not the largest possible filament, but rather the largest one identified and measured with certainty. There may be even longer structures, vast superhighways of matter connecting different regions of the universe, filaments so large that they span the entire observable universe. But 50 million light-years is already almost incomprehensibly large. To give perspective, the Milky Way galaxy is only about 100,000 light-years across. This filament is 500 times the diameter of our galaxy, yet it is still only one of many such structures in the cosmic web. Filaments are the largest coherent structures in the universe. They are larger than galaxy clusters, larger than superclusters when measured individually. Though superclusters can be made up of multiple filaments and their intersections, they are the true scaffold upon which the universe is built. They are the framework into which all smaller structures fit. Understanding filaments is key to understanding the overall organization of the universe. Galaxy clusters form at the intersections of filaments, where multiple cosmic highways meet and matter concentrates into extremely dense regions. Where 2 or 3 or 4 filaments converge, matter accumulates. Gravity overwhelms the expansion of space. The matter cannot escape. It is pulled together by the combined gravitational effects of all the surrounding mass. These clusters can contain hundreds of galaxies or thousands of galaxies bound together by gravity. A dark matter halo, invisible but massive, holds them together. All the galaxies orbit around their common center of mass. These clusters represent the densest regular structures in the universe. They are islands of matter in a sea of space, but they are not solitary islands. They are connected to each other and to other structures through the filaments. The densest regions of clusters mark perhaps the most violent, the most chaotic places in the universe, where structure has coalesced to the highest degree. In these regions, galaxies collide with each other. Their stars pass through each other's collections, interacting gravitationally. Galaxies merge, their stars becoming part of a new, larger galaxy. Gas flows between galaxies, fueling intense star formation. Black holes at the centers of galaxies may collide and merge. These regions are dynamic, violent, chaotic. They are the least peaceful parts of the universe. Scientists have developed sophisticated algorithms to map and understand the cosmic web. Some of these algorithms are inspired by slime mold growth, by the way single-celled organisms navigate their environment and find the most efficient paths. Slime molds, despite lacking brains or nerves, can solve complex optimization problems. When placed in a maze, they will find the shortest path. When resources are scattered, they will find the most efficient way to connect them. Scientists realized that the algorithm by which slime molds accomplish this optimization is similar to the physics of matter flowing along gravitational gradients in the cosmic web. Gravity creates gradients in space-time, and matter flows along these gradients toward regions of high density. By applying slime mold-inspired algorithms to galaxy survey data, astronomers can identify filaments and trace their paths through space, revealing the geometry and structure of the cosmic network. The universe, it seems, follows patterns that echo organic life, suggesting deep connections between the organization of matter at all scales. The patterns that emerge in the cosmic web on the largest scales are the same patterns we see in biological systems, in river networks, in neural networks. This may not be coincidence. It may reflect deep principles of organization and efficiency that operate across all scales and all types of systems. The web's structure is hierarchical. This means that smaller structures are embedded within larger ones, creating a nested architecture that repeats at different scales. Galaxies cluster together into groups, which cluster into larger clusters, which sit along filaments that make up the cosmic web. At each level, gravity has organized matter into structures. The process of organization is not uniform. There is a natural scale above which the universe becomes homogeneous, a scale that marks the transition from structure to randomness. This scale is called the end of greatness. Part 4. The architecture of structure. The end of greatness occurs at a scale of approximately 100 megaparsecs. A megaparsec is a unit of distance equal to 1 million parsecs, and 1 parsec is about 3.26 light-years. 100 megaparsecs is therefore about 326 million light-years. This is the scale where the large-scale structure becomes homogeneous. At scales larger than 100 megaparsecs, filaments and voids average out, and the universe begins to look the same everywhere. Below this scale, gravity has had time to organize matter into the complex structures we see. Filaments, clusters, voids, and galaxies all exist at scales smaller than the end of greatness. This is one of the most important thresholds in cosmology because it marks the limit of cosmic structure formation. It is the boundary between a structured universe and a homogeneous universe. It tells us that the universe is not infinitely complex, infinitely detailed, infinitely structured. Beyond a certain scale, the structure ceases. The details average out. The universe becomes smooth and uniform. This end of greatness supports the cosmological principle and validates our fundamental assumptions about the nature of the universe. It tells us that if we zoom out far enough, the universe looks the same everywhere. Now, at the largest scales of structure, we find superclusters. Superclusters are the largest gravitationally bound structures in the universe. A supercluster might span hundreds of millions of light-years, containing multiple galaxy clusters, countless filaments and subfilaments, billions of galaxies, and incomprehensible numbers of stars. These structures are held together by gravity, though the binding is often tenuous. The gravitational attraction between different parts of a supercluster is not always strong enough to hold them together indefinitely. In fact, many superclusters are not actually gravitationally bound at all. They are just chance associations, collections of clusters that happen to be near each other but are not orbiting around a common center of mass. The expansion of the universe will gradually separate them. Over cosmic timescales spanning trillions of years, some superclusters that are currently associated may eventually disperse, moving away from each other as space expands. One of the largest and most famous superclusters is the Sloan Great Wall. This is one of the largest known superstructures, stretching across approximately 500 million light-years of space. To put this in perspective, this single structure is nearly as large as the entire observable universe would be if light could only travel 100 million light-years through space, if expansion were much slower, if the universe were much younger. The Sloan Great Wall represents one extreme of the cosmic structure, a testament to just how large matter distributions can become through the process of gravitational clustering. The cosmic web is far more than just a snapshot of the current universe. It is a fossil record of cosmic flows and galaxy formation. By studying the structure, the positions, and the motions of galaxies within the cosmic web, astronomers can reconstruct how matter has flowed throughout cosmic history. They can see the paths that galaxies have followed, the trajectories they have taken, the convergences and divergences that have shaped their evolution. Galaxies that were far apart in the past have come together through the cosmic web's structure. Filaments that form today may break apart in the distant future. The cosmic web is dynamic, ever-changing, a record of billions of years of structure formation and evolution. Matter flows along filaments into clusters, and this flow fuels star formation. When gas falls into regions of high density, when it accumulates along filaments and into clusters, it can cool and condense into stars. The rate at which matter flows along filaments helps determine the rate at which new stars form in galaxies. The cosmic web is not merely a passive structure through which matter moves. The structure actively influences how that matter behaves. Filaments channel gas, concentrate it, create conditions suitable for star formation. The cosmic web is thus not merely a static structure, but a dynamic system where matter constantly moves, where energy flows, where the universe is actively creating new structures and new possibilities. Filaments can influence the spin and evolution of galaxies in ways that we are still working to understand. When a galaxy forms along a filament, when it assembles its stars and gas along one of these cosmic highways, it tends to have its axis of rotation aligned with the filament. This is not random. The geometry of the filament influences the geometry of the galaxy. The filament's shape influences the galaxy's shape. This means that filaments can determine the orientation of galaxies, the direction in which they spin, the shape they take. Over time, as galaxies interact with the filament and with each other, these rotations and alignments influence how galaxies evolve, how they grow, and what form they ultimately take. The cosmic web's geometry is shaped by dark matter, which provides the scaffolding for visible matter. Dark matter is a mysterious form of matter that does not interact with light, that does not emit or absorb radiation, that is essentially invisible to our telescopes. Yet dark matter has mass, and mass produces gravity. Dark matter outweighs ordinary matter by a factor of about 5 to 1. It is the dominant form of matter in the universe, and it is dark matter that creates the gravitational structure into which visible matter settles. The filaments we see, made of galaxies and gas, are nested within the invisible filaments of dark matter. The voids we observe correspond to regions where dark matter is sparse. Dark matter is the architect, and visible matter is the decoration, the artwork painted onto the dark matter's framework. Part 5. The Ancient Light. From the vast scales of the cosmic web, let us now turn our attention to the ancient light that fills all of space, the cosmic microwave background, one of the most precious and revealing pieces of evidence in all of science. This is light that has been traveling through the universe for longer than galaxies have existed, longer than stars have shone. This is the voice of the infant universe, speaking to us across billions of years of cosmic history. The cosmic microwave background is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang. In the very beginning, the universe was inconceivably hot, far hotter than the core of the Sun, far hotter than any temperature we can produce in laboratories on Earth. In this environment, matter could not exist in the form we know. Atoms could not form. Electrons and protons were unbound, free particles colliding with each other and with photons in a chaotic, turbulent plasma. But the universe was not static, it was expanding. As the universe expanded, it cooled. The temperature dropped. After about 380,000 years, the temperature had fallen to about 3000 Kelvin. At this temperature, something remarkable happened. Electrons and protons combined to form neutral hydrogen atoms in an event called recombination. For the first time since the Big Bang, atoms could exist in a stable state. This recombination was profound because of its effect on light. Before recombination, the universe was opaque. Light could not travel far before being absorbed by charged particles. Light was constantly being emitted and absorbed in a chaotic dance. But once recombination occurred, once electrons combined with protons to form neutral atoms, the universe became transparent. Charged particles were no longer free to scatter photons. Light could travel freely. Photons released at recombination began their journey through the expanding universe. These photons, unchanged in their fundamental properties, are the cosmic microwave background. Today, after 13.8 billion years of traveling through the expanding universe, this ancient light has cooled dramatically. The cosmic microwave background is now a nearly uniform blackbody radiation at a temperature of 2.725 Kelvin. Kelvin is an absolute temperature scale where 0 Kelvin represents the complete absence of heat, the point at which all thermal motion ceases. 2.725. Kelvin is extremely cold, only about 2.7 degrees above absolute zero. At this temperature, matter would be frozen solid. Any ordinary materials would be brittle, frozen, immobile. This light, ancient and cold, fills all of space and time. It is not localized in any region, it is everywhere. There are about 400 photons of cosmic microwave background radiation in every cubic centimeter of space. 400 ancient photons, relics of the early universe, in a volume the size of a sugar cube. If you could somehow see this radiation, if you could become sensitive to microwave wavelengths, you would find yourself swimming in an ocean of ancient light, surrounded by this ancient radiation in all directions. But this light is not perfectly uniform. Despite its name, the cosmic microwave background has tiny temperature fluctuations, slight variations in temperature from place to place. These anisotropies are incredibly subtle, about 1 part in 100,000. If the overall average temperature is 2.725 Kelvin, the variations are typically about 10 millionths of a Kelvin. These are incredibly subtle differences, difficult to measure, requiring sensitive instruments and careful analysis. It took until 1992 for instruments to develop to the point where these fluctuations could be definitively detected. Yet these tiny fluctuations are perhaps the most important features in all of cosmology. These fluctuations are the seeds of all large-scale structure. The regions that are slightly hotter in the cosmic microwave background correspond to regions of slightly higher density in the early universe. These denser regions attracted more matter through gravity. Over billions of years, gravity amplified these tiny variations, turning them into galaxies, clusters, and the entire cosmic web. Without these initial fluctuations, the universe would be perfectly uniform, with no places for stars to form, no places for galaxies to exist, no places for complexity to emerge. Life as we know it would be impossible. These microscopic variations in temperature, barely measurable, are the fountains from which all complexity flows. The cosmic microwave background provides a snapshot of the universe at a specific moment in time, the moment of recombination, approximately 380,000 years after the Big Bang. This snapshot reveals what the universe was like in its infancy, before structure had formed, before gravity had sorted matter into galaxies and clusters. It is a picture of the universe when it was young, hot, and nearly uniform. By studying the cosmic microwave background, we are looking backward through time, seeing the universe as it was when it was in its earliest stages of development. The cosmic microwave background comes from a spherical shell called the surface of last scattering. This is the spherical shell from which the photons that make up the cosmic microwave background originated. It is not a surface in physical space that we can touch or reach. Rather, it is a surface in space-time, a moment in the past, as seen from our current location. When we look in any direction, we are looking toward this spherical shell, but at different distances. Photons that reach us from the direction of the constellation Virgo, for example, have traveled from the surface of last scattering in that direction. The entire cosmic microwave background surrounds us, a spherical halo of ancient light centered on our position. And this is true from every location in the universe. Every observer from every location sees themselves at the center of their own cosmic microwave background sphere. This is not a violation of the cosmological principle. Rather, it is a natural consequence of the isotropic and homogeneous nature of the universe. The cosmic microwave background's power spectrum, the measurement of how temperature fluctuations vary with scale, reveals profound information about the universe. The power spectrum is calculated by analyzing the temperature map of the cosmic microwave background and determining the amplitude of temperature fluctuations at different angular scales. Large angular scales correspond to large structures in the early universe. Small angular scales correspond to small structures. By examining the pattern of peaks and valleys in the power spectrum, we can determine the properties of the early universe. The first acoustic peak in the power spectrum determines the overall curvature of the universe. Acoustic peaks arise from sound waves that propagated through the early universe. These sound waves were created by the pressure of radiation pushing against the gravitational attraction of matter. The competition between pressure and gravity created oscillations in the density of matter. These oscillations imprint themselves as peaks in the power spectrum. The location of the first peak depends on the curvature of the universe. If the universe is flat, the first peak occurs at a specific location in the spectrum. If the universe were closed, curved like the surface of a sphere, this peak would shift to higher frequencies. If the universe were open, curved like a saddle, the peak would shift to lower frequencies. Measurements of the cosmic microwave background have confirmed that the universe is indeed flat within the limits of our ability to measure. The second and third peaks in the power spectrum reveal the densities of baryonic matter, which is ordinary matter made of protons and neutrons, and dark matter. Different compositions of the universe produce different patterns of peaks and valleys in the power spectrum. If the universe contained more ordinary matter relative to dark matter, the peaks would be taller and shorter at different scales. If it contained more dark matter relative to ordinary matter, the pattern would shift. By comparing the observed power spectrum to theoretical predictions for different matter compositions, scientists can determine the abundance of different types of matter in the universe. These measurements have shown that ordinary matter makes up about 4.8% of the universe, dark matter makes up about 27%, and dark energy makes up about 68%. The cosmic microwave background exhibits something called polarization, which means that the light waves oscillate in particular directions rather than randomly. Unpolarized light has photons oscillating in all directions. Polarized light has photons oscillating preferentially in one direction or in one plane. The polarization of the cosmic microwave background can be divided into E-mode and B-mode patterns. E-mode polarization arises from the scattering of light by free electrons in the early universe, after reionization but before recombination. B-mode polarization, if detected, could indicate the presence of primordial gravitational waves, ripples in space-time created in the earliest moments of the Big Bang, in the period of cosmic inflation. The search for B-mode polarization is an active and exciting area of cosmology research. If B-modes are detected and confirmed to be of primordial origin, this would be revolutionary. It would provide direct evidence of cosmic inflation and would reveal something about the energy scale of inflation, the temperature and energies in the universe's first fraction of a second. Several experiments are currently searching for this signal, including BICEP and other sensitive instruments. As of now, the B-mode signal has not been definitively detected, though the search continues. Part 6. The uniformity of the ancient skies. The cosmic microwave background is isotropic to about 1 part in 25,000. Isotropic means that it looks the same in all directions. If you were to measure the temperature of the cosmic microwave background in different directions across the sky, comparing the intensity of radiation from opposite sides of the sky, you would find that they are nearly identical. The difference is about 1 part in 25,000. This means the cosmic microwave background is about 250 times more uniform than the tiny temperature fluctuations we discussed earlier, which are 1 part in 100,000. This remarkable uniformity confirms the cosmological principle on the largest scales. It shows that the universe does not have a preferred direction or a special location. If the universe had a preferred direction, The cosmic microwave background would be stronger in that direction and weaker in the opposite direction. If the universe had a special location, different locations would see different cosmic microwave background properties. Instead, we find uniformity. Every observer from every location would perceive essentially the same cosmic microwave background. This is a profound statement about the fundamental nature of the universe. Yet there is a subtle exception to this uniformity. The cosmic microwave background exhibits what is called a dipole. The dipole is a systematic pattern of warmer light coming from one direction and cooler light from the opposite direction. The dipole is not a feature of the universe itself, not a sign that the universe is not homogeneous. Rather, it is a feature of our motion through the universe. It is caused by the motion of our solar system relative to the cosmic microwave background rest frame. As we move through space, the cosmic microwave background light ahead of us appears slightly blue-shifted, warmed, due to the Doppler effect. Light from a source that is moving toward you appears shifted to shorter, bluer wavelengths if the source is hot and appears brighter and warmer. Light from a source that is moving away from you appears shifted to longer, redder wavelengths and appears dimmer and cooler. Because our solar system is moving through space, we are moving toward the light coming from one direction of the cosmic microwave background and away from the light coming from the opposite direction. This creates an apparent dipole in the cosmic microwave background. The dipole tells us our velocity relative to the cosmic microwave background rest frame, our motion through the fabric of space-time. The cosmic microwave background is the most precisely measured blackbody spectrum in nature. A blackbody is an idealized object that emits radiation according to its temperature, following specific mathematical laws discovered by Max Planck at the beginning of the 20th century. The spectrum of radiation emitted by a blackbody depends only on its temperature. No other details matter. A blackbody at 2.725 Kelvin will have a specific spectrum of radiation. The cosmic microwave background's spectrum matches the blackbody prediction so closely to better than 1 part in 10,000 that it confirms the universe was once in thermal equilibrium. In thermal equilibrium, all regions have the same temperature, and light is constantly being emitted and absorbed. The cosmic microwave background's perfect blackbody spectrum is strong evidence that the early universe was indeed in this state. The uniformity of the cosmic microwave background supports the cosmological principle in the most fundamental way. It tells us that in the early universe, all locations were essentially equivalent. There was no privileged location, no center, no special place where the Big Bang occurred. This insight that the universe has no center is one of the most profound and humbling revelations of science. We are not at the center of the cosmos. The Earth is not at the center. The Sun is not at the center. The galaxy is not at the center. Every location in the universe is equivalent. Every location is, in a sense, the center of its own observable universe. But here is a profound puzzle that has troubled cosmologists for decades. The cosmic microwave background anisotropies are coherent on scales larger than the apparent horizon at recombination. The apparent horizon is the maximum distance light could have traveled since the Big Bang up to the moment of recombination. Regions separated by more than twice this distance could never have been in contact with each other, never have exchanged light or signals, never have reached a common temperature or equalized their properties. Yet the cosmic microwave background shows the same temperature, the same properties, in regions that were separated by more than twice this horizon distance. How is this possible? How can regions that never had time to exchange light have the same temperature? This is the cosmic horizon problem, one of the deepest puzzles in cosmology. The currently accepted explanation invokes cosmic inflation, a period of extraordinarily rapid expansion in the first fraction of a second after the Big Bang. During inflation, the universe expanded so rapidly that distant regions that are now separated by more than the horizon distance were actually brought into contact. They had time to equilibrate, to reach common temperatures and properties. Then, as inflation ended and normal expansion resumed, these regions were pulled apart again, but they retained the common properties they had acquired during the inflationary period. This inflation hypothesis is compelling because it solves not just the horizon problem, but also the flatness problem and several other puzzles about the initial conditions of the universe. But inflation remains a theoretical framework that is not yet definitively proven. Different models of inflation make different predictions, and we are still searching for observational evidence to distinguish between them. The search continues, and this remains an area of active research and theoretical exploration. Measurements of the cosmic microwave background have provided insights into another profound mystery. The CMB's angular power spectrum is sometimes called a Rosetta Stone for cosmology because it contains so much information about the universe. From this single dataset, scientists have been able to determine the age of the universe, its composition, its geometry, and many other fundamental properties. The power spectrum is like a fingerprint of the universe, encoding information about its past, its present, and its fundamental nature. Future measurements of the cosmic microwave background will continue to refine these estimates and potentially reveal new physics beyond our current understanding. Certain cosmic phenomena have been constrained or ruled out by cosmic microwave background measurements. For instance, cosmic microwave background measurements rule out cosmic strings as a major structure formation mechanism. Cosmic strings are theoretical topological defects, one-dimensional objects of extremely high density that might have formed in the early universe if certain types of phase transitions occurred. They would be stretched to tremendous lengths and would remain after the phase transitions. These strings would leave distinctive signatures in the cosmic microwave background's power spectrum. Specifically, they would create anomalies, disturbances in the power spectrum at specific scales. Because no such distinctive signatures are observed, we can conclude that cosmic strings, if they exist at all, did not play a significant role in creating the structures we see today. This is a powerful constraint that has ruled out or severely limited certain theoretical models of the early universe. The cosmic microwave background's spectrum is consistent with adiabatic density perturbations. Adiabatic means that the ratio of matter to radiation remains constant during the perturbations. This is important because different types of initial fluctuations would produce different patterns in the cosmic microwave background. If the initial fluctuations were isocurvature perturbations, where different types of matter had different initial conditions, the pattern would be different. But the observed pattern matches adiabatic perturbations. This means that the initial fluctuations in the early universe were generated in a way that conserved the overall properties of the matter radiation system. This is consistent with fluctuations generated by quantum mechanics in the very early universe, which is what inflation theory predicts. Finally, the cosmic microwave background's small-scale anisotropies are damped or reduced in amplitude by two effects. One is diffusion of photons, which tends to smooth out small-scale temperature variations. Photons can travel between different regions, carrying energy and heat, which tends to equalize temperatures. The other effect is the finite thickness of the surface of last scattering. The transition from an opaque universe to a transparent one did not happen instantaneously at a single moment, but rather took place over a finite period of time, perhaps a few 100,000 years. This finite thickness means that photons from different depths within this transition region have slightly different travel distances to reach us. This difference in travel distances washes out the smallest scale temperature differences. These damping effects help determine the fine structure of the power spectrum and provide information about the properties of matter and radiation in the early universe. Part 7. The Cosmic Expansion. We have journeyed from the vast structures of the cosmic web to the ancient light that surrounds us, and now we turn our attention to one of the most profound discoveries in all of science. The universe is expanding, not just expanding in the sense that space is being created and pushed outward, but accelerating in its expansion, speeding up, driven by a mysterious force that permeates all of space and time. The universe's expansion is accelerating due to dark energy. Dark energy is perhaps the greatest mystery in modern physics. We know it exists because we can measure its effects. We can see that it causes the expansion of the universe to speed up. We can write equations that describe its behavior. We can make predictions about the future evolution of the universe based on our understanding of dark energy. But what it fundamentally is remains unknown. We do not know if it is a genuine form of energy, a property of space itself, a modification of gravity on cosmic scales, or something entirely different. Dark energy behaves as though space itself has an intrinsic energy density, a property called the vacuum energy or the cosmological constant. This energy density does not decrease as the universe expands, unlike ordinary matter, which becomes more dilute as space stretches. This is the key property that makes dark energy's effects cumulative and eventually dominant. In the early universe, when space was smaller and more densely packed with matter and radiation, the effects of dark matter and ordinary matter dominated. But as the universe expanded and matter became more dilute, dark energy's effects became relatively more important. Eventually, dark energy became the dominant force shaping the expansion. If dark energy remains constant, as current observations suggest, then the universe will continue to accelerate its expansion indefinitely. In the remote future, billions of trillions of years from now, when light from the most distant galaxies has long since left the observable universe, dark energy will still be there. still accelerating the expansion, still driving the universe toward an infinite, cold, empty future. The universe will continue to grow, space will continue to stretch, galaxies will continue to move apart, and eventually, in a timescale almost incomprehensibly distant, the universe will be so dilute, so cold, so empty, that all complexity will fade away. The rate at which the universe expands is measured by something called the Hubble constant. Despite its name, the Hubble constant is not constant in the sense of being unchanging throughout cosmic history. Rather, it is constant in space, meaning that all locations in the universe have the same expansion rate at any given time. But its value changes with time as the universe evolves. The universe was expanding faster in the past when dark energy was less important relative to matter. It will expand faster in the future as dark energy becomes ever more dominant. The current value of the Hubble constant is approximately 67.74 kilometers per second per megaparsec. This measurement and its precise value was determined through careful observations of distant objects. This means that a region of space 1 megaparsec away from us is moving away at a velocity of 67.74 kilometers per second due to the expansion of the universe. A megaparsec is about 3.26 million light-years, so we can say that the universe expands at a rate of about 67 kilometers per second for every 3.26 million light-years of distance. The expansion rate is slowing down due to gravity, but accelerating due to dark energy. This statement captures the essential dynamic of cosmic expansion. Gravity, the attractive force between all matter and energy, tends to slow expansion. Matter pulls on matter. Galaxy pulls on galaxy. The entire universe pulls on itself. This gravitational attraction acts to slow the expansion rate. If only gravity were operating, the expansion would eventually stop and the universe would begin to contract. But this was a profound discovery made in the late 1990s by observations of distant supernovae. Astronomers expected to find that the expansion was slowing down due to gravity. Instead, they found that expansion was accelerating. This observation contradicted expectations. It revealed the existence of dark energy and its dominance over gravity on cosmic scales. It was such an unexpected result that the discoverers were awarded the Nobel Prize in Physics in 2011, more than a decade after the discovery. For most of the history of the universe, gravity, the attractive force between all matter and energy, was slowing down the expansion. Matter was more densely packed. The gravitational effects were stronger. The expansion rate was decreasing over time. But as the universe expanded and matter became more spread out, gravity's effects weakened. Meanwhile, dark energy, which seems to have a constant density, remained important. The balance shifted. About 5 billion years ago, which was only recently in cosmic history, dark energy overtook gravity as the dominant force shaping the expansion of the universe. Since then, expansion has been accelerating. The universe is speeding up, not slowing down. The expansion rate determines the size of the observable universe. In a universe that expanded very quickly, very early on, objects would have moved far away before light had time to reach us from them. The observable universe would be smaller. In a universe that expanded more slowly, light would have had time to reach us from farther away. the observable universe would be larger. The specific expansion history of our universe, as determined by the balance of matter, radiation, and dark energy at different times, determines the size of the sphere within which we can observe. The expansion rate affects the geometry of the universe. In general relativity, the expansion rate is related to the density of matter and energy in the universe through Einstein's field equations. These equations are mathematical relationships between the geometry of space-time and the distribution of matter and energy. A universe with more matter would expand more slowly, its gravity stronger, and could be closed, curving in on itself like the surface of a sphere. A universe with less matter would expand faster, its gravity weaker, and could be open, curving away from itself like a hyperbolic surface. Our universe, with the density of matter and energy it contains, expands in such a way that the overall geometry is flat. This flatness is not accidental. It follows from the specific combination of matter density and expansion rate. The expansion rate determines the fate of the universe. This is perhaps the most profound implication of understanding cosmic expansion. Different possible futures for the universe correspond to different expansion scenarios. In one scenario, gravity might eventually overcome expansion and pull everything back together in a big crunch, a reverse Big Bang where all matter collapses to infinite density. In another scenario, expansion could continue forever, though perhaps slowing down, eventually reaching a maximum size. In yet another scenario, expansion could accelerate indefinitely, driving galaxies apart until they become infinitely separated, until light from one galaxy can never reach any other galaxy. Which of these futures we are moving toward depends on the expansion rate at each moment in cosmic history. The expansion rate determines the universe's destiny. Current evidence suggests that dark energy will cause the universe to expand forever, growing cold and dark over unimaginable timescales. The fate of the universe appears to be one of infinite expansion and eventual heat death. But this remains an area of active research, and our understanding continues to evolve. The expansion rate is not measured directly by looking at how fast the universe expands right now. That would be extremely difficult. Rather, it is inferred from observations using several complementary methods. Astronomers observe distant supernovae, explosions of stars at cosmological distances. Type Ia supernovae, in particular, are valuable because they result from the thermonuclear explosion of a white dwarf in a binary system. And this process produces explosions of roughly consistent brightness. This makes them standard candles for measuring cosmic distances. By measuring the brightness and redshift of these supernovae, astronomers can determine their distance and velocity. Redshift is the shift toward longer, redder wavelengths that light experiences when the source is moving away from us. The farther the source, the greater the redshift due to cosmic expansion. By measuring redshift, astronomers can infer velocity. By combining velocity with distance measurements from the brightness of the supernova, they can determine the expansion rate. Astronomers also use baryon acoustic oscillations, which are preferred scales in the distribution of galaxies created by sound waves in the early universe. These sound waves propagated through the primordial plasma before recombination. They left imprints in the matter distribution that are visible in modern galaxy surveys as a slight excess of galaxy pairs separated by a specific distance. This distance acts as a cosmic ruler. By measuring this ruler at different times in cosmic history through the redshifts of galaxies, astronomers can measure how space has expanded at different times. This gives information about the expansion rate at different epochs. The cosmic microwave background also provides information about the expansion rate. The size and pattern of the acoustic peaks in the power spectrum depend on the expansion rate at the time of recombination. By analyzing these peaks, scientists can infer what the expansion rate was 13.8 billion years ago. Combined with measurements at more recent times from supernova and baryon acoustic oscillations, this gives a comprehensive picture of how the expansion has changed throughout cosmic history. The expansion rate varies with time, as we have discussed. It was different in the early universe and is different today. But within any given time period, is the expansion rate uniform throughout space? To some extent, yes. The cosmological principle tells us that the universe is homogeneous and isotropic on large scales, which means the expansion rate should be the same everywhere at any given time. However, on smaller scales, there are variations due to local matter distributions. Where there is more matter, gravity is stronger, and the local expansion rate can be slightly slower. Where there is less matter, the local expansion rate can be slightly faster. But these variations are small, and on the largest scales, the expansion rate is indeed uniform. Part 8. The Cosmic Destiny. The expansion rate is used to calculate several fundamental properties of the universe that determine its past, present, and future. Understanding expansion is the key to understanding everything about the cosmos. Using the expansion rate and its history, we can calculate the age of the universe. Cosmologists observe distant supernovae and other objects at various distances, and they measure their redshifts. This gives information about how fast the universe was expanding at different times in the past. By observing objects at different redshifts, they build up a picture of the expansion history. They can see how the expansion rate was greater at high redshifts in the distant past than it is today. They can determine when the expansion started to accelerate due to dark energy dominating over gravity. By analyzing this expansion history, by running the history backward from today to the past, they can determine how much time has elapsed since the Big Bang. They add up all the time increments going backward, and they arrive at a total age for the universe. Current measurements place the age of the universe at approximately 13.8 billion years, with an uncertainty of about 1%. This means the universe is 13,800,000,000 years old, plus or minus about 100 million years. The expansion rate is used to calculate the size of the observable universe. We have already discussed how the observable universe has a radius of approximately 46.5 billion light-years. But how do we arrive at this number? We use the expansion history. We calculate how far light could have traveled given the age of the universe and the changing expansion rate. We take into account that while light was traveling toward us, the space carrying it was expanding, pulling the light's origin point farther away. We integrate over all of cosmic history accounting for how the expansion rate changed at different times. The result is the size of the observable universe, the radius of the sphere from which light has had time to reach us. The expansion rate is used to calculate the mass-energy density of the universe. By observing how the expansion rate changes with time, or equivalently, how the expansion rate changes with redshift, astronomers can infer the composition of the universe. Different types of matter and energy have different effects on the expansion rate. Matter and radiation slow expansion down, contributing negative pressure that decelerates expansion. Dark energy speeds expansion up, contributing negative pressure in the opposite sense, repulsive pressure that accelerates expansion. By carefully measuring the expansion rate across a range of distances and times, comparing observations at low redshifts and high redshifts, scientists can determine how much of each type of component makes up the universe. They can separate the effects of matter and dark energy. They can estimate the density of ordinary matter and dark matter. The measurements show that the universe's total mass-energy density corresponds to a critical density that makes the geometry flat. And the breakdown is approximately 4.8% ordinary matter, 27% dark matter, and 68% dark energy. The expansion rate is used to calculate the geometry of the universe. The density of matter and energy, combined with the expansion rate, determines the geometry of space-time through Einstein's field equations. These equations are the cornerstone of general relativity. They relate the geometry of space-time to the distribution of matter and energy. A flat universe, a closed universe, and an open universe all have different expansion histories and different relationships between density and expansion rate. By measuring the expansion rate and the density of matter and energy, we measure the geometry. Current measurements show our universe to be flat, at least within current observational limits, as we have discussed multiple times throughout this journey. The expansion rate is also used to calculate the fate of the universe, which is perhaps the most profound application of this fundamental parameter. The far future of the universe is determined by how dark energy evolves and how dominant it remains over the next trillion years and billions of years beyond that. If dark energy remains constant, as it appears to be based on current observations, then the universe will continue to accelerate its expansion indefinitely. What will this mean for the distant future? In the unimaginably distant future, billions of trillions of years from now, the universe will be cold, empty, and dark. Galaxies will have moved so far apart that light from one galaxy can no longer reach any other galaxy. Each galaxy will be isolated in its own expanding bubble of space. Stars will have burned out. All the nuclear fuel will be exhausted. Electrons and protons may eventually decay into radiation, though this is not certain. The universe will be dominated by radiation, by particles, by emptiness, and by the continued expansion driven by dark energy. Yet understanding the expansion does not just tell us about the distant future. It tells us about ourselves. We live in a universe that is expanding and accelerating. This means that the galaxies we see today will eventually become invisible to observers in the distant future. The light from distant galaxies will be so redshifted that it will be beyond detection. Future civilizations will inherit a much smaller observable universe than we have inherited. Part 9. The Horizons of Observation. As we continue our journey through the cosmos, we must discuss the boundaries of what we can see and know, the cosmic horizons that define the limits of reality as we experience it. These horizons are not walls or barriers, not physical obstacles that we might someday overcome. Rather, they are the mathematical limits imposed by the structure of space-time and the nature of light itself. They define the universe as we can ever hope to understand it. The particle horizon is the maximum distance from which light has had time to reach us. It defines the edge of the observable universe. Any object beyond the particle horizon is, by definition, unobservable. We cannot see light from it. We cannot receive information from it. We cannot know anything about it directly. We can speculate about what lies beyond the particle horizon. We can imagine what those regions might be like, but we cannot observe them, or measure them, or interact with them in any way. The particle horizon is approximately 46.5 billion light-years away. This is the radius of the sphere of the observable universe. It surrounds us in all directions. It is not a physical boundary. Space does not end there. The universe does not end there. But our observational access to the universe is limited by the particle horizon. The particle horizon defines the observable universe in the most literal sense. The observable universe is everything within the particle horizon. It is a sphere centered on the observer with a radius equal to the particle horizon distance. Every atom we can see, every star, every galaxy, every photon we can detect, everything we know through observation lies within this sphere. Beyond this horizon lies the unknowable, the unobservable, the cosmic mystery that we may never comprehend. The particle horizon is larger than the age of the universe times the speed of light due to expansion. Light travels at a constant speed of approximately 300,000 kilometers per second. The universe is 13.8 billion years old. If the universe were not expanding, light could have traveled only 13.8 billion light-years in that time. But the universe is expanding. While light was traveling toward us from distant objects, the space carrying it was stretching, expanding, pulling the light's origin point farther and farther away. Imagine a photon leaving a distant galaxy near the beginning of the universe 13 billion years ago. As it travels toward us at the speed of light, the space it is traveling through is expanding. The galaxy that emitted it is being carried away by this expansion. By the time the photon finally reaches us, the galaxy has moved much farther away than 13 billion light-years. The photon has traveled 13 billion light-years, but the galaxy is now much more distant due to the expansion. The particle horizon is finite but unbounded. Finite means it has a definite size, a maximum distance. We cannot see objects that are infinitely far away. There is a limit to how far we can look. Unbounded means there is no wall, no edge, no boundary to space itself at the particle horizon. The observable universe has an edge, but space extends beyond that edge. Space continues beyond the particle horizon, filled with matter and galaxies and the cosmic web. It is a subtle but profound distinction. The observable universe is finite. Space itself may be infinite, The particle horizon is the same in all directions. We live at the center of our observable universe, not because Earth or the Milky Way or our galaxy cluster is special, but because this is how observation works. Light takes time to reach us. The most distant objects we can see are those from which light had just enough time to reach us since the universe began. This creates a sphere around us. The farthest we can see in all directions is the same distance because we are looking back in time to roughly the same epoch, the era of recombination, when the cosmic microwave background was emitted. The universe at recombination was approximately the same age and the same size in all directions relative to us. The particle horizon is centered on the observer. Every observer in the universe has their own particle horizon, their own observable universe centered on their location. This does not mean that different observers see entirely different universes. The observable universes of observers separated by nearby distances overlap significantly. But there are distant galaxies that are observable from one location but not from another. From those distant galaxies' perspective, we are beyond their particle horizon, invisible and unobservable. The universe is infinitely large and infinitely interconnected, yet from any given vantage point, we can observe only a finite portion of it. The particle horizon is limited by the speed of light and cosmic expansion. Light, the fastest thing in the universe according to Einstein's special relativity, sets the ultimate speed limit. Nothing can travel faster than light, so nothing can reach us from farther than light could travel. But cosmic expansion also plays a role in determining the particle horizon. Even if light travels at its maximum speed, the expansion of the universe can push its starting point farther away as the light travels toward us. The interplay between light speed and expansion determines the size of the particle horizon. The particle horizon is used to calculate the size of the observable universe, the age of the universe, the mass-energy density, the geometry, and the fate of the universe. All of these fundamental properties depend on understanding the particle horizon, on understanding how far we can see and what that tells us about the cosmos. Part 10. From Structure to Infinity. As we move toward the conclusion of our extended journey into the cosmos, let us bring together the threads we have woven throughout this voyage. We have traveled from the smallest scales of structure we can measure to the grandest vistas our instruments can perceive. From the flatness of space-time itself to the vast filaments of the cosmic web. From the ancient light of the cosmic microwave background to the mysterious dark energy driving cosmic acceleration. We have explored how structures form, how light propagates, how time unfolds in an expanding universe. The universe's expansion is accelerating due to dark energy. This simple statement contains within it the trajectory of our cosmic future. The expansion is not slowing down under the pull of gravity. It is speeding up. Space itself is stretching faster and faster. The universe is driving apart at an ever-increasing rate. The universe's expansion will continue indefinitely. There is no reversal, no bouncing back, no return to a prior state. The arrow of cosmic expansion points forever forward into the future. Backward, we can trace the arrow to the Big Bang, to the moment of infinite density and infinite temperature. Forward, the arrow points toward an infinitely distant future of infinite expansion and infinite emptiness. In 1 trillion years, the universe will be larger and more dilute than it is today. Galaxies will be farther apart. Space will be colder. The density of matter will be spread over an ever larger volume. In 1 trillion years, it will be larger still, even colder, even more dilute. The universe will become progressively emptier, progressively colder, progressively darker. The universe's expansion will eventually cause all galaxies to move beyond the observable horizon. Every galaxy we see today, every galaxy we know exists, will eventually move so far away that light from them will no longer reach us. The expansion of space will carry them away faster than light can reach us. This is not a violation of relativity. Light still travels at the speed of light through space, but space itself is expanding so rapidly that the distance light must cross grows faster than light can traverse it. This means the universe's expansion will eventually cause all galaxies to become invisible to observers in the distant future. The sky will go dark. The light of galaxies will be so red-shifted, so stretched, that it will be pushed beyond the range of any possible detector. Galaxies will appear to fade from view, not because they are disappearing, but because expansion is carrying them away faster than light can reach any observer. Future civilizations will see a much smaller and darker universe than we do. Our cosmic neighbors will become ghosts, theoretical objects we know are out there but can never observe. The idea that there are galaxies out there that we could never see, could never reach, could never know except through our calculations is somehow both profound and melancholy. The universe will become progressively more lonely as expansion isolates galaxies from each other. The expansion will eventually cause all galaxies to become unreachable. Even if future civilizations had the technology to send spaceships at nearly the speed of light, they would never be able to reach distant galaxies. The expansion of space would carry those galaxies away faster than any ship could travel toward them. This is not a limitation of technology or engineering. It is a fundamental feature of space-time itself, a consequence of gravity and the laws of general relativity. The universe will fragment into isolated island universes, each galaxy surrounded by its own dark horizon, unable to see or interact with neighbors. Each galaxy will become a solitary island in an ever-expanding sea of empty space. The networks of filaments that bind galaxies together will be stretched and broken. The cosmic web will unravel. Galaxies that are currently neighbors will be separated beyond the reach of light or any causal connection. The expansion will eventually cause all galaxies to become undetectable. After visibility is lost through redshift, the concept of detection must be reconsidered. Without light, without any information-carrying signal, distant galaxies become beyond reach of observation, beyond reach of knowledge. They will exist somewhere out in the expanded universe, but they will be unknowable. They might as well not exist from the perspective of any observer. The expansion will eventually cause all galaxies to become unobservable in any meaningful sense. The word unobservable takes on a profound significance. It does not just mean we cannot see them. It means we cannot know anything about them. We cannot exchange signals with them. We cannot verify their existence. We cannot know that they have not undergone some dramatic transformation. They will be beyond the scope of any possible science. Yet within the observable universe, within the sphere centered on us, with a radius of 46.5 billion light-years, structures remain. Within the cosmic web of filaments and voids, galaxies continue their ancient dance, shaped by gravity and dark matter, guided by the complex interactions of cosmic forces. Stars are born and die. Planetary systems are created and destroyed. Life emerges where conditions allow. Chemistry creates complexity. Consciousness arises and contemplates existence. This is the universe in which we live, the observable cosmos that defines our cosmic home. It is a universe of vast scales, from the Planck length to the Hubble radius. It is a universe of extreme conditions, from the density of neutron stars to the emptiness of voids. It is a universe of both structure and simplicity, complexity and uniformity, chaos and order. Part 11. The Cosmic Fossil Record. As you continue to rest, as sleep begins to draw near, allow your mind to explore how the universe has grown and structured itself over billions of years. The story of cosmic structure formation is one of the most profound narratives science can tell us. A story of how the universe evolved from near-perfect uniformity to the complex, beautiful structures we observe today. Large-scale structure formed from small density fluctuations in the early universe. In the first moments after the Big Bang, the universe was incredibly hot and incredibly dense, but it was not perfectly uniform. Quantum fluctuations, the random variations permitted by quantum mechanics at the smallest scales, created tiny variations in the density of matter and radiation. These fluctuations were incredibly subtle, variations of perhaps 1 part in 100,000. Yet these variations contained within them the seeds of all future structure. They contained the blueprints from which galaxies, stars, planets, and life would eventually emerge. They were the fountains from which all complexity would flow. The universe's history is the story of how these microscopic variations grew through the patient action of gravity into the grand structures we observe today. Gravity amplified these fluctuations over time. In regions slightly denser than average, gravity pulled in more matter, making them even denser. This self-reinforcing process continued for billions of years. What began as microscopic variations became regions of slightly higher concentration, then clumps of matter, then proto-galaxies, and finally the galaxies we see today. Gravity is the great amplifier, the force that took whispers of variation and shouted them into the structures we observe. This process of gravitational amplification follows from Newton's law of universal gravitation and from the equations of fluid dynamics. Where density is higher, gravity is stronger. More gravity means more attraction, which pulls in more matter, which increases density further, which increases gravity further. It is a feedback process, a vicious cycle of increasing concentration. Over billions of years, this feedback process transforms the tiniest fluctuations into structures spanning millions of light years. Dark matter played a crucial role in structure formation. Though dark matter is invisible, it comprises about 85% of all matter in the universe. the gravitational influence of dark matter exceeds that of ordinary matter by a factor of 5 or 6. Therefore, dark matter's gravitational effects overwhelmingly dominated the process of structure formation. Dark matter clumped first, creating a gravitational scaffold. Ordinary matter, responding to the gravity wells created by dark matter, then collected within these dark matter structures. It is as though the universe built the house out of dark matter first, and then ordinary matter moved into the house. The dark matter framework determines where ordinary matter collects. The dark matter scaffold shapes the cosmic web. The visible matter, the matter that forms stars and galaxies, decorates the dark matter structure. The first stars and galaxies formed approximately 100 to 200 million years after the Big Bang. This was remarkably quick on cosmic timescales. The universe had existed for less than 2% of its current age, yet it had already produced the first stellar objects. These early stars were massive and short-lived, far more massive than our Sun, burning through their fuel in only a few million years. They were extremely luminous, shining with the light of millions of suns. When they died, they exploded as supernovae, scattering their material into space and creating heavy elements. These early stars were crucial because they were the universe's first element factories. Stars create heavy elements in their cores through nuclear fusion. Our Sun fuses hydrogen into helium. Massive stars create heavier elements: carbon, oxygen, silicon, iron. The very heaviest elements are created in supernova explosions. These early stars fused light elements into heavier elements, enriching the universe with the chemical diversity necessary for planets and life. Without these early stars, the universe would still be made of only hydrogen and helium, the lightest elements. There would be no carbon, no oxygen, no silicon, no iron. There would be no rocky planets. There would be no chemistry. There would be no complexity. We would not exist. Our very atoms were forged in the hearts of dying stars billions of years ago. We are made of stardust, of the ashes of stellar furnaces. Galaxy formation is hierarchical, with small structures merging into larger ones. The first galaxies were small, containing perhaps billions of stars. Over time, through gravitational attraction, these small galaxies merged with their neighbors, forming larger galaxies. Those larger galaxies merged with others, forming even larger structures. This process continues today. We can observe it happening in the universe around us. Galaxies collide and merge, their stars becoming part of a new, larger system. Merger is a violent process. When galaxies collide, their stars pass through each other's collections. Most stars miss each other because space is mostly empty. But some stars are deflected, their orbits changed by the gravitational influence of the merging galaxy. The galaxy's gas clouds collide directly, compressing and heating. The compressed gas can trigger intense star formation. Black holes at the centers of galaxies may collide and merge into larger black holes. The Milky Way itself was formed through mergers and is currently in the process of merging with the Andromeda Galaxy. This merger will take billions of years to complete. In the distant future, perhaps a few billion years from now, the Milky Way and Andromeda will fully merge into a single, larger galaxy, sometimes called Milkomeda or Milkdromeda. This merger is not violent in any absolute sense, but it will rearrange the orbits of stars and compress the galactic structure. The cosmic web itself is the result of gravitational collapse in the early universe. As matter clumped together and separated into regions of high and low density, filaments formed along the paths where matter concentrated. Voids formed in the spaces between filaments. This pattern was inevitable, given the initial conditions and the laws of gravity. It was not designed or engineered. It emerged naturally from the physics of a universe responding to gravitational attraction. Filaments and voids formed as matter collapsed into overdense regions. Matter did not collapse uniformly. It did not condense equally everywhere. Instead, it flowed preferentially into certain regions, following the gravitational gradients created by the initial density fluctuations. Where matter concentrated, it formed filaments. Where matter was depleted, voids opened up. This created the web-like structure we observe today, a structure that has remained recognizable for billions of years, even as individual structures within it have changed. The largest structures are limited by the age of the universe and the speed of light. This is a profound constraint on cosmic architecture. A structure cannot be larger than the distance light could travel since the universe began. The largest galaxy clusters and superclusters are approaching these limits. Some of the largest known structures are nearly as large as the observable universe could be, given our current understanding of cosmic history. This represents a fundamental constraint on cosmic architecture imposed by the finite age of the universe and the finite speed of light. Part 12. The Tapestry of Cosmic Time. The end of greatness marks the scale where structure becomes homogeneous. We have discussed this before, but it bears repeating as we consider the hierarchy of structure and the limits of cosmic organization. Below 100 megaparsecs, the universe is clumpy and structured. Above this scale, the universe appears smooth and uniform. This transition is one of the most important facts about the universe's architecture. It tells us that the universe is not infinitely structured, not infinitely detailed, not infinitely complex at all scales. Beyond a certain size, the details average out and uniformity emerges. The cosmic web's geometry is shaped by both gravity and cosmic expansion. These are the two primary forces acting on the universe on large scales. Gravity pulls matter together, creating structures, creating filaments, and clusters and galaxies. Expansion pulls matter apart, creating voids, limiting the size of gravitationally bound structures. The balance between these forces determines the form the cosmic web takes. In a universe with more dark energy, expansion dominates, and structures are smaller and more isolated. In a universe with more matter, gravity dominates, and structures are larger and more interconnected. Galaxy clusters form at the intersections of filaments. Where multiple filaments meet, where multiple streams of matter converge, the density is highest. Gravity here overwhelms the expansion of space. The matter cannot escape. Multiple filaments funnel matter into these cluster regions. The result is the densest regular structures in the universe. Galaxy clusters are perhaps the most massive gravitationally bound structures, containing hundreds or thousands of galaxies and dark matter halos, millions or billions of times the mass of our Milky Way. The cosmic web's structure can be mapped using galaxy surveys. Large surveys like the Sloan Digital Sky Survey have catalogued millions of galaxies and their positions. By plotting these positions in three-dimensional space, using redshift to determine distances, astronomers can see the cosmic web directly. The surveys reveal filaments stretching across billions of light years, clusters at their intersections, and vast empty voids between them. These maps are among the most beautiful outputs of modern astronomy, showing the structure of the cosmos in stunning clarity. If you could zoom out and view the cosmic web from a distance, if you could see all the galaxies and filaments and voids at once, you might be reminded of organic structures. The network of blood vessels in a body, the branching of a river system, the structure of a brain with its network of neurons. This is not coincidence. It reflects deep principles of organization and efficiency that operate across all scales and all types of systems. The cosmic web's geometry influences galaxy evolution. As galaxies move through the cosmic web, they experience different influences. Galaxies in dense clusters experience frequent encounters with their neighbors. Interactions that can trigger star formation, merge galaxies together, or disrupt their structure entirely. Galaxies in filaments experience gentler interactions, occasional encounters with nearby galaxies. Galaxies in voids are isolated and experience minimal interaction. The environment a galaxy lives in determines much about its history and current state. A galaxy that has lived in a dense cluster, its entire existence will have evolved differently from a galaxy that has lived in a void. Cluster galaxies are often elliptical, relatively featureless, with older stellar populations and little ongoing star formation. Void galaxies tend to be spiral or irregular, with younger stellar populations and active star formation. The cosmic web is not just a structure, it is a determinant of galactic destiny. Matter flows along filaments into clusters, fueling star formation. The flow of matter through the cosmic web is not static. Gas and dark matter continually flow along filaments toward the densest regions, toward the cluster cores. This flowing matter brings fuel for star formation. When gas accumulates and cools, when it radiates away its energy and contracts under gravity, it forms stars. The rate of matter flow along filaments therefore determines, to some extent, the rate of star formation in galaxies and clusters. Where matter flows, stars are born. The cosmic web is a dynamic system of flows and counterflows, a living, evolving structure. Matter flows in along filaments toward clusters. It heats up through compression and shock waves. Some of it is blown back out into space by energy released by supernovae and active galactic nuclei. Some of it settles into the cluster, forming stars, cooling, accumulating. The balance between inflow and outflow, between cooling and heating, determines how galaxies grow and evolve. The cosmic web is a fossil record of cosmic flows and galaxy formation. By studying the structure we see today, by measuring how galaxies move and how their properties vary across the cosmic web, we can reconstruct its history. The shape of the cosmic web encodes information about how matter has flowed and where it has accumulated. Galaxies within the cosmic web show signatures of this history in their properties, their motions, their compositions. The cosmic web's structure is hierarchical, with smaller structures embedded in larger ones. We have discussed this concept before, and we return to it now because it is perhaps the most important point about cosmic organization. At every scale we examine, we find a nested hierarchy. Atoms contain particles. Particles make up atoms. Atoms cluster into molecules. Molecules form matter. Matter clumps into stars. Stars cluster into galaxies. Galaxies cluster into groups. Groups cluster into clusters. Clusters sit along filaments. Filaments comprise the cosmic web. This hierarchy is not accidental. It emerges naturally from the process of gravitational collapse, acting on initially small variations. Whenever you have density variations and gravity, you will get hierarchical structure. At every scale, gravity amplifies variations, creating structures, which are then embedded in larger structures, which are themselves embedded in even larger structures. The universe naturally organizes itself into a nested hierarchy. The cosmic web's geometry is shaped by dark matter, which provides the scaffolding for visible matter. We have touched on this before, and we return to it now because it is perhaps the most important point about cosmic structure. The universe we see, the galaxies and stars and planets we observe, make up only about 15% of all matter. 85% is dark matter, invisible and mysterious. This dark matter provides the gravitational skeleton upon which visible matter hangs. Without dark matter, there would be no structure. Ordinary matter alone without dark matter would not clump strongly enough to form galaxies. The gravitational attraction of ordinary matter is not strong enough. It is dark matter's gravity that provides the scaffolding that allows ordinary matter to collect and form structures. Without dark matter, galaxies would not hold together. Stars would not orbit in the patterns we observe. The cosmic web would not exist. The universe we see is secondary, a decoration painted onto the dark matter architecture. Imagine sculpting a statue. First, you shape the rough form out of stone. Then you add details, paint colors, add final touches. The cosmic web is like this. Dark matter is the stone, the basic structure. Ordinary matter is the paint, the decoration, the details. We see the decoration, but the structure is dark matter. The cosmic web's structure can be mapped using algorithms inspired by slime mold growth. This is one of the more delightful facts about modern cosmology. Slime molds are single-celled organisms that, despite lacking brains or neurons, can solve optimization problems. They find efficient paths through mazes. When resources are scattered, they find the most efficient way to connect them. When conditions worsen in one location and improve in another, they rearrange themselves accordingly. Scientists realize that the algorithm by which slime molds accomplish this optimization is similar to the physics of matter flowing along gravitational gradients in the cosmic web. Gravity creates gradients in space-time, and matter flows along these gradients toward regions of high density, following the most efficient paths. The universe and the slime mold are solving the same optimization problem, though at vastly different scales and with completely different mechanisms. By applying slime mold-inspired algorithms to galaxy survey data, astronomers can identify filaments and trace their paths through space, revealing the geometry and structure of the cosmic network with greater efficiency and accuracy. The cosmic web's geometry can be probed using gravitational lensing. We have mentioned this technique before. Massive structures in the cosmic web bend light through their gravity, much as a glass lens bends light through refraction. Photons follow the curvature of space-time created by massive objects. When light from distant galaxies passes near massive structures, its path bends. The distant galaxy's image is distorted, magnified, or split into multiple images. By observing how light from distant objects is bent, astronomers can map the distribution of matter, both visible and dark, along our line of sight. Gravitational lensing allows us to see the dark matter distribution indirectly through its effects on light. It has become one of the most powerful tools for mapping the cosmic web and understanding its structure. The cosmic web's structure is a key test of cosmological models. Different theories about the nature of dark matter, the history of inflation, the properties of dark energy, all make different predictions about the structure of the cosmic web. By comparing observations of the cosmic web to predictions from different theories, scientists can test and refine their models of the universe. The cosmic web is thus not merely an interesting feature of the universe, but also a laboratory for testing our fundamental understanding of how the universe works. As we come to the end of this extended journey through the cosmos, we find ourselves having traveled from the most intimate scales of quantum fluctuations in the early universe to the grandest vistas of cosmic evolution. We have seen how the universe is organized at every level, how structure emerges from simplicity, how complexity arises from the interplay of gravity and the fundamental laws of physics. We have contemplated the shape of the observable universe, from its fundamental flatness to its complex web-like structure. We have traced the evolution of the universe from the Big Bang to the present day and gazed into the distant future. The observable universe, that sphere of 46.5 billion light-years surrounding us, contains everything we can ever hope to know directly. It contains galaxies numbering in the trillions, stars numbering in the septillion. It contains the cosmic web of filaments and voids, stretching across billions of light-years. It contains the ancient light of the cosmic microwave background, whispers from the early universe. It contains us, conscious beings capable of understanding the universe that created us. Beyond that sphere lies mystery. Beyond the particle horizon lies mystery. But within that sphere lies wonder enough to occupy curious minds for countless generations. The cosmic web continues to evolve, driven by forces we are still working to understand. Dark energy continues to accelerate the expansion. Stars continue to form and die. Galaxies continue their slow dance toward merger and transformation. The universe continues its march toward an infinite, cold, empty future. The shape of the observable universe, that flat sphere of cosmic light, continues to define the limits of what we can know. You are part of this universe. Your consciousness is the universe becoming aware of itself. Your understanding of these vast structures and cosmic processes is the universe studying itself. This is not metaphor or poetry, though it is poetic. This is literal truth, grounded in the physical processes by which consciousness emerges from matter and energy. Every atom in your body was forged in stellar furnaces. Every molecule in your brain follows the same physical laws that govern galaxies. You are connected to every star, every galaxy, every structure in the cosmic web. As you continue to rest, as your mind settles into the peaceful spaces between waking and sleep, carry with you the knowledge that you are at home in this cosmos, that you belong here, that your existence is a temporary but real part of the universe's eternal drama. The observable universe expands, the cosmic web grows, time moves forward toward futures of unimaginable remoteness. And in this moment, in this place, you rest knowing that you are among the most remarkable structures in the universe. A conscious being, capable of wonder, capable of understanding the universe that created you. Sleep well, traveler of the cosmic ocean. Sleep well, child of the stars. May your dreams be peaceful and your rest be deep. The universe will still be here when you awaken, just as it has been since the beginning, just as it will be until the end of time itself. You are home in the cosmos. You are part of the eternal dance. You are the universe experiencing itself. Rest now and know that you are exactly where you belong.